Uranus is not only an extraordinary planetary outlier but also a significant mystery in scientific research. This isn't surprising, considering the shimmering blue ice giant has only been visited up close by Voyager 2, leaving researchers with limited data. Despite this, scientists have recently uncovered several astonishing and perplexing characteristics of Uranus. The planet orbits the Sun while tilted on its side, its magnetic field boasts not just 2 but 4 poles, and its surface temperature is an unexpectedly frigid -216 degrees Celsius. However, astronomers have now made progress in unraveling the mysteries surrounding Uranus, particularly its unusual 4-pole magnetic field, which may be linked to remarkable processes occurring deep within the planet. Additionally, the Uranus system has expanded. Just months ago, experts announced the discovery of a previously unknown moon orbiting the distant ice giant. This finding has increased the number of Uranus's known moons from 27 to 28, and fittingly, the newly detected satellite is the smallest of them all. Initially designated as S223U1, this small celestial body measures just 8 kilometers across. However, the lingering mysteries surrounding Uranus for decades make it all the more intriguing. As mentioned earlier, the most recent data we have on this peculiar ice giant still comes from 1986. Yet, despite its age, the information collected by Voyager 2 continues to reveal new surprises. One of the most striking discoveries from Voyager's data was an unexpectedly intense radiation belt teeming with energetic, fast-moving electrons within Uranus' magnetosphere. The strength of these particle currents was comparable to those in Jupiter's extreme magnetosphere. However, unlike the gas giant, Uranus appeared to lack the plasma source necessary for generating such electrons. This was particularly perplexing, given that the 5 largest moons of Uranus should have been continuously releasing water molecules into space, molecules that, in theory, would become ionized by the planet's magnetosphere. For decades, scientists wrestled with these puzzling findings. Only now have they uncovered an explanation for these unusual conditions. Astonishingly, the key to this astronomical breakthrough had been hiding in the old data all along, simply overlooked. That changed when a research team led by Jami Jeansky at NASA's Jet Propulsion Laboratory revisited the Voyager 2 data. The probe had not only analyzed the radiation and particle density during its Uranus flyby but also in the days before and after, ultimately shedding new light on this long-standing mystery. Shortly before Voyager 2's passage, a powerful solar storm struck Uranus, compressing its magnetic field and stripping away surrounding plasma into space. While this event disrupted the magnetosphere, it also flooded the planet's radiation belt with high-energy electrons. In essence, Voyager 2 happened to catch Uranus at an unusual moment rather than in its normal state. Experts believe that if the probe had arrived just a few days earlier, the magnetosphere would have appeared entirely different. However, in a way, Voyager 2's timing was remarkable. Such extreme conditions are estimated to occur only about 4% of the time. Interestingly, diamonds are believed to reign inside Uranus. While solving this nearly 40-year-old plasma mystery marks a significant step in understanding the planet, Uranus' exotic magnetic field still poses major challenges for scientists. But how does a planet's magnetic field form in the first place? On Earth, which has a typical dipole magnetic field, this phenomenon results from convection currents in the liquid outer core, working in conjunction with the solid iron core to create a geodynamo. A dipole field, with 2 opposite poles, requires a sufficiently thick convective layer. However, Uranus appears to lack this necessary thickness. Models suggest that the planet's unusual, non-dipole magnetic field could be generated if these currents are restricted to a thin outer layer. Additionally, we know that Uranus' interior consists of a solid core surrounded by a mix of water, ice, ammonia, and methane, substances that may be conductive, making them potential sources of a convective dynamo. What remains unknown, however, is the exact structure of Uranus' lower layers and what might be obstructing the deep planetary currents responsible for its magnetic field. One theory suggests that water inside Uranus exists in an exotic superionic state, where oxygen atoms form a solid lattice while hydrogen ions move freely within it. Another, even more fascinating theory, one that would thrill any jeweler, proposes that it might actually rain diamonds inside Uranus. The immense pressure and temperature deep within the ice giant could be enough to break down hydrocarbons, compressing carbon into diamond crystals. This diamond rain may also help explain the planet's unusual multipolar magnetic field. As diamonds descend, they drag gas and ice with them, creating convection currents in the mantle. The movement of conductive molecules in this process could contribute to Uranus' peculiar magnetic properties. While these ideas seem plausible, recent research suggests a different explanation. Instead of superionic water or diamond rain, the mystery of Uranus' magnetic field might stem from distinct, non-mixing layers within the planet's interior. This fresh perspective comes from Burkhard Militzer of the University of California, Berkeley. Using high-resolution computer simulations, the Dresden-born scientist modeled the behavior of methane, water ice, and ammonia under Uranus' extreme conditions, offering new insights into the planet's enigmatic magnetic field. What was special about this was the fact that, thanks to an adaptive algorithm, Militzer was able to simulate the processes with atomic precision for the first time, with a surprising result. When the professor of Earth and planetary science looked at the model, the water had separated from the carbon and nitrogen. As a result, several layers were created that cannot mix with each other. At the very top is a conductive layer of water and ammonia about 8,000 kilometers thick, which is probably partly liquid. This is also the area where the convective currents take place, which act as the engine of the multipolar magnetic field. Just below that, there is a similarly thick zone of nitrogen-containing hydrocarbons whose hydrogen content decreases with increasing depth and pressure, ultimately resulting in several layers of these compounds that become steadily denser. According to Militzer, this circumstance prevents vertical flow, which is why these layers cannot play a significant role in the formation of Uranus's magnetic field. In other words, the hidden interior of the planet behaves like oil and water, and the bottom line is that the division into two emiss layers can explain why Uranus has such an exotic magnetic field. But as is so often the case, the theory still needs to be put to the test in the course of future investigations.